Hey people! So today I went into the interwebs to search for some fun papers on OpenSees. What are some creative things people are doing with OpenSees? I want to see stuff getting done with OpenSees, far beyond the regular scope of OpenSees. So OpenSees is a very powerful finite element simulation framework. All sorts of things happen in OpenSees. I've seen space simulations. I've seen micro models for masonry. I've seen metamaterials. I've seen earthquake engineering. All sorts of things going on. Even fluid structure interaction simulation going on in OpenSeas is awesome. So I went to the internet to see what is the most out there thing that I could find, and I found this fun paper by Sunku Kang, Jennifer G. Dai, and Michael B. Kane. I'm sorry if I messed up those last names, but they're from the Department of Civil and Environmental Engineering at Northeastern University in Boston. And this was published in the Journal of Artificial Intelligence for Engineering Design, Analysis, and Manufacturing. It's stone masonry design automation via reinforcement learning. So out of the box, it doesn't come up as something that is open seas. But here's the fun part. What these guys are actually doing is they're playing Tetris. They came up with this fun little game called MasonTris, where they build structures, masonry structures, and the finite element engine that runs behind this is, you guessed it, OpenSea. So this is a fun little idea. I had fun reading this. So they start off with a little background on how masonry construction it has a high dependence on domain knowledge. Basically, I guess, builders, people that build things out of masonry, they're experts. They know how to lay their bricks, right? That's bricklaying is their thing. And so how do you get an artificial intelligence to learn how to do this without this prior expert knowledge? And they use OpenSeas as a driver for this. So let's quickly take a look at what's going on here. So basically, they're modeling pieces of stone masonry as you would Tetris, what I call it, polyominoes. So if a domino, a D-omino is a two blocks, polyomino is several blocks. In particular, a tetromino is these Tetris type shapes. So the idea is that you will stack these masonry pieces on top of each other and stick them together with mortar, right? And then you can evaluate using some physics engine the factor of safety of this. And if you can run this enough times, you can figure out, or you can teach a system to lay bricks, essentially. Lay bricks. This is fun. So the idea, this is how it looks like. This is kind of like the implementation. You have a design space, which is a board, and they assume here that the nodes that are at the bottom, those are fixed, and then you apply a vertical pressure at wherever the top is, right? And the system will try to use different tetrominos to explore different configurations of the design space, so different possible brick layouts, so to speak. So the idea is to identify the strongest design among the lightest design, satisfying the predefined safety constraint without prescribed knowledge. So they have a metric of reward, which involves factor of safety, but it also involves the weight of the structure. So the lightest structure will tend to win. So and we can skip all the details with regarding the machine learning. It's not my strong. But here's a little bit of what the environment looks like. But basically, what they do is you stack up a bunch of boards. These get stuck together, and you identify areas which are brick. So the blues are brick, and then you have one to specify the mortar area, and -1 would specify the empty area. And then a finite element analysis gets run on this. You get deformation. And from the deformation, you can compute stresses. And from that, you can compute a performance score of the resulting stone masonry structure. This is kind of how it looks like. You have the vertical pressure on top, and you have standard 8-node bricks. And they do consider linear elastic analysis for each of these steps. And you can kind of see what the system is looking at here. It has this is showing, I believe, the vertical stress at different points, but I assume that they actually compute the factor. Actually, they do compute the factor using the principal stresses at each element. So basically, this is a measure of, okay, so P1, it would be the first principal stress at a brick, and this one would be the secondary principal stress. So this one would be tension, this one would be compression, and they compare those with the resistance, a predefined resistance. So this is a simple rule to compute a safety factor, and they compute that over the whole structure, and then the minimum value of all of these will be the safety factor. So that has to be above 2. So you can see here they can compute stresses for each of these structures and then compute a score. And then the reward actually gets mapped into something that takes into account weight. So they go through this whole thing. Here's an example MasonTris problem. You have several bricks and you have to compute the best possible layout for this. Now this is what the artificial intelligence has to figure out. So they train this, and they use some sort of semi-greedy algorithm to basically not be calling OpenSees all the time, because this is a key part. Like, calling OpenSees for each of these simulations is expensive, so you wouldn't want that. So what they do is that they do it as minimally as possible, so that they don't have huge training times. So this is the kind of results they're getting. Here's the progression of stone masonry design under the proposed framework for the design problem shown here, right? And the figure, you see, you can fill the space with bricks and you'll get a reward of 2.2, and your safety factor will be 3.03. But then if you form columns, your safety factor might go down, but you'll get a lighter structure, so you get a higher reward. And then if you actually do one column instead of 2, but you kind of add a capital on top, so you basically thicken out at the top, you can get a higher reward with a lower safety factor. So this is kind of human behavior. If you say the safety factor is 2, we will try our best to get as close to that safety factor as possible without being below it, because we know the closer we are, we're using our materials more effectively. So we don't want to waste materials. We don't want a safety factor of 2.1. We want a safety factor of 2, and be able to be as economically as possible. So I thought this paper was awesome. Actually, this is the kind of thing I want to see. I'm interested in seeing in OpenSees people doing things that are kind of out of the box, and this kind of inspires me. I might want to come up with a game that a kind of a Tetris game that uses this concept. Might be the subject of a future video, but for sure, what I've been wanting to do for some time is to do some short videos reviewing some papers on OpenSees or otherwise awesome civil engineering papers. And this is maybe the first in that installment of series. I really want to be on top of the literature, so this might also help you out. So if you have awesome papers that I might be interested in reviewing, just send them my way. I'd be happy to take a look at them. So until the next time, I hope you enjoyed this one.